Now, what we said was, we considered actually pictorially five different characterizations of concavity and convexity of functions. Now, the first one was, now this will be 3.2, the section, concave and convex functions. Now, this is a typical concave function from R to R, and if this is X, this is Y, we formed, taking these 2 points on the graph, the secant line. And we said the secant should be less than or equal to the graph. It should stay. Now, that means, and this portion, this line segment, take any point in here. What will that be? Well, that actually, for some lambda, that will be, this is not the segment xy, this will be lambda x plus 1 minus lambda y. This will be the value of f of lambda x plus 1 minus lambda y. But that will be this. Now here, this secant line lying below the graph means that this distance should be less than or equal to this larger distance, which is equal to this. But this now is a combination of f of y and f of x with the same proportion. So this part is lambda f of x plus 1 minus lambda f of y. So defining a concave function by the condition that for any xy in the domain, for any lambda in the unit interval, that f of lambda x plus 1 minus lambda y, this value, should be larger than or equal to lambda f of x plus 1 minus lambda f of y is nothing but the translation of this picture into formal terms. We'll take that as our definition as well. Now, let V be a real vector space and C a non-empty subset of V, but we'll take that to be convex. Well, because for this condition to make sense, if x and y are in the domain of the function, which will be C here, then the segment from x to y, that is lambda x plus 1 minus lambda y, for any lambda in the unit interval, that should be in C as well. So we'll take the domain as a convex subset of V. Now let f on C to R be a function. We actually refer to real-valued functions, convex or concave, or some version of that. Okay? Now, we say that f is first concave if for all x, y in C, for all t, let me take it 0, 1, because if t is 1 or 0, equal to 1 or 0, this will be either x or y, but f of x and f of y, and well, that will be the same. So you have equality. So we don't need to check at the endpoints of the unit interval. In fact, let me erase this. F of tx plus 1 minus ty is larger than or equal to tf of x plus 1 minus t f of y. We say that f is convex if all this holds, but this time the inequality is reversed. We say that this is strictly concave if, now here, well, let me write it in full, for all t in 0, 1. Well, no matter where I take t in this open or closed interval, if x and y are the same, then these two sides will be equal to each other. So for strict inequality to hold here, I have to rule out the case where x is equal to y. That is, x different than y implies f of tx plus 1 minus ty is larger than tf of x plus 1 minus t f of y. For strictly convex, if all this holds, but this time the inequality is reversed. Let me turn back to the first color. 5. Quasi-concave if for all x, y in C, for all t in 0, 1. Now here we take ftx plus 1 minus ty and require what to happen? That this quantity is larger than or equal to the minimum of the two f of x and f of y. Min f of x, f of y. Then 6, it's said to be quasi-convex if this holds, this here gets reversed, but this gets reversed as well. Now you have the maximum of f of x and f of y. Next, strictly quasi-concave. if, well, we have for all xy in C, for all t in 0, 1, f of t, again, if x and y are the same, well, the minimum will be f of x equal to f of y. These will be the same, and this will be f of x or f of y. But then you'll have equality. So again, x different than y, that should imply that f of tx plus 1 minus ty, this is larger than the minimum of f of x, f of y. And finally, 8. Strictly quasi-convex if all this holds, this is less than the maximum of f of x, f of y. Okay? So these are all definitions you're familiar with. Now, we again can have a simple proposition consisting of statements, all statements being familiar to you. But let's have it so that we can refer to it. Proposition. Let V be a real vector space and C in V convex F on C to R a function. Now, 1, F is convex respectively, strictly convex respectively, quasi-convex respectively, strictly quasi-convex, if and only if minus F is concave, the red version, strictly concave, the black version, quasi-concave, the green version, strictly quasi-concave. Well, of course, this also implies, well, F is concave if and only if minus F is convex and so on. That's okay. Secondly, F is strictly concave implies F is concave, and that implies F is quasi-concave. And of course you have the convex version of this. F is strictly convex, implies F is convex. That implies F is quasi-convex. And thirdly, which is also clear, F is strictly quasi-concave, implies F is quasi-concave, and F is strictly quasi-convex. That implies F is quasi-convex. Now, proof obvious. Okay, so we are over with the tedious part.
Can we imply strict quasi-concave by strictly concave function?
Say it again.
Can we imply strict quasi-concave function from strict concave function? Because we'll have the definition that x and y will be different.
Yeah.
And we can have...
But I mean, there are quasi-concave functions which are not strictly quasi-concave. Like what, for example, from R to R? Just take y equals x. Y equals x from R to R is everything. It's concave, it's convex, it's not strict, the non-strict versions. It's quasi-concave, quasi-convex, but for the strict version. Is that the answer to your question? Where can we, here, strict concavity implies concavity. Okay?
I meant like at part 2, we say F is strictly concave.
Yeah.
Why does that not imply F being strictly quasi-concave?
Yeah, that implies, so there is, that is missing in here. Yeah, that implies, okay. Okay, well then let me do that. F is strictly concave, implies F is strictly quasi-concave, and F is strictly convex. That implies F is strictly quasi-convex. Okay. So you're saying if you write everything, this is also okay. Otherwise, well, one might doubt whether that's not true or not. Thanks. The second characterization, that was if you have a concave function, then the region below its graph, that was a convex subset of R2, if the function is from R into R, and for the concave function, what remains above. But here, of course, this is in R cross R. Now, if our function is on a non-empty convex subset of a real vector space, that will be in V cross R. But from the first exercise set, we know that if you take two real vector spaces, if you form their product, their Cartesian product, and extend the binary operations on V1 and in V2 in an appropriate manner, in a component-wise manner, the resulting object, that will be a real vector space again. But let me start by reminding you of that. Now let V1 with the operations plus and dot, addition, vector addition, and scalar multiplication. Let's take them circled. V2, again, with two operations, be real vector spaces. Now set V equal to V1 cross V2 for any x1, x2, y1, y2 in V1 cross V2, that is in V, define x1, x2 plus y1, y2 as follows. x1 and y1, they're in V1. We add them according to the vector addition of the first space. x2 and y2 are in V2. We add them according to the vector addition in the second space. And here, let's take any C in R here as well, and define C x1, x2 as first C, here this scalar product with x1, and here C, this scalar product with x2. Now, V plus dot is a real vector space again. So the real vector space V, one of whose subsets will be the domain of our function, the range is R, that's also a real vector space. Then V cross R under this will also be a real vector space. Thus we can talk convexity of its subsets, because that's what we'll need in this characterization. Now, let V be a real vector space and C a non-empty subset of V. Now, to define the subgraph and the epigraph as we will refer to them, I don't need the convexity of the domain. Let f on C to R be a function. We define the epigraph and denote that f of f by now this will consist of points x, y, where x is in C, in the domain of the function, and y is in R. Now, the epigraph is this. Well, if you take a point in here, if this is xy, now what happens here is y is larger than or equal to f of x. We define the subgraph sub f of f by subgraph of f xy in C cross R, but this time y should be less than or equal to f of x. It will be something in here. This is x, this is y, but y should be less than this f of x in this case. Now we can have our characterization. Let V be a real vector space. C, a non-empty convex subset of V. F on C to R, a function. Firstly, F is concave. Let me leave some space for convex. If and only if subgraph of F is a convex subset of C cross R. Now, F is convex if and only if epigraph of F is a convex subset of C cross R. Secondly, we can also characterize quasi-concavity and quasi-convexity of the function given in terms of convexity of some subsets of V this time. F is concave if and only if for all real numbers R, the set of all x in C such that f of x is larger than or equal to R is a convex subset of V or of C, but the real vector space is V. This is, I'm sorry, quasi-concave, of course, not is quasi-concave, and here it's quasi-convex if and only if for all R in R, this time we'll have x in C such that f of x is less than or equal to R is a convex subset of V. Here, in each case we have 4 different statements, but they're all similar to each other. So for this, we will prove that concavity of F implies that the subgraph is a convex subset of C cross R. And here, well, if this blue condition holds, then that implies quasi-concavity of the function. The rest is similar, and that will be left to you as an exercise. 1. Assume that F is concave. Now what we need to show is that the subgraph of f is a convex subset of here. So what we'll do is we'll take 2 points in the subgraph of f and some lambda. We'll take their convex combination with lambda and 1 minus lambda being the coefficients and show that the resulting convex combination belongs to the subgraph again. Okay? So assume that x1, y1, x2, y2, that these belong to the subgraph of f and lambda is in 0, 1. Well, what does it mean that these are in the subgraph? Then f of x1, that is larger than or equal to y1, and f of x2, that is larger than or equal to y2. What we wish to show is that lambda times this plus 1 minus lambda times this, that's in the subgraph as well. But according to the definition, lambda times this plus, well, let me write that, note that lambda x1, y1 plus 1 minus lambda x2, y2, that this is equal to lambda x1 plus 1 minus lambda x2, and this is lambda y1 plus 1 minus lambda y2. Now, what do we know about this? x1 and x2, they belong to C. If these are in the subgraph, x1 and x2 belong to the domain of the function, but C is convex. This is in C since C is convex. This is in R. Well, actually, since R is convex, but it suffices to note. So this is in C cross R. In order to conclude that this combination belongs to the subgraph as well, all we need to show in addition is that f of this combination is larger than or equal to the second component. Now, f of lambda x1 plus 1 minus lambda x2. What do we know? What's our assumption about f? That it's concave. So this is larger than or equal to lambda f of x1 plus 1 minus lambda f of x2. This since f is concave. But what do we know about f of x1? It's larger than or equal to y1. F of x2, that's larger than or equal to y2. And lambda and 1 minus lambda, they are both non-negative. So this is larger than or equal to lambda y1 plus 1 minus lambda y2. But this simply means, let me continue here, thus lambda x1, y1 plus 1 minus lambda x2, y2, that belongs to the subgraph of f. Because that combination is equal to this. This is in C, this is in R, and f of the first component, that's larger than or equal to the second component. That's just the definition of subgraph of f. So subgraph of f is convex. Rest for part one exercise. Now let's consider part two. Any questions about this? Okay. This time, let us take something in the reverse direction. Well, to prove something for concave and convex functions is the same because you take just the negative of that. So let's assume the right-hand side blue statement. Assume that for all real numbers R. Now let me give a name to this set. A sub R equal to x in C such that f of x is larger than or equal to R is convex. Now this should imply that f is quasi-concave. To show that f is quasi-concave, take xy in C, lambda in 0, 1. What shall we show? Well, that f of lambda x plus 1 minus lambda y, that's larger than or equal to the minimum of f of x and f of y. But that's what we know for all R. What R, the convexity of what set seems to be appropriate here, if I take this, I want to show that lambda f of x plus 1 minus lambda, f of lambda x plus 1 minus lambda y is larger than or equal to the minimum of f of x, f of y. And I will use the convexity of these sets. But these are for all R. What R seems to be, to the point here, appropriate here, just the minimum of f of x and f of y. Set R equal to the minimum of f of x, f of y. By hypothesis, A sub R is convex. But if R is equal to the minimum, since how are f of x and R related? F of x is larger than or equal to R. F of y is larger than or equal to R. Because this is equal to just either f of x or f of y, and we have this with one equality. That is, well, that means x is in A sub R, y is in A sub R as well. xy in A sub R, implying that what's our assumption about A sub R? It's convex. So lambda x plus 1 minus lambda y is in A sub r, since A sub r is convex. Okay? Well, what does that mean? So, f of lambda x plus 1 minus lambda y, that's larger than or equal to r. That's what it means, this belonging to A sub r, but that was the minimum of f of x, f of y. So, f is quasi-concave. Again, rest is similar, and that's left as an exercise too. Again, a simple result. Now, concavity says, well, take any xy, f of lambda x plus 1 minus lambda y, that's larger than or equal to the convex combination of f of x and f of y with the same coefficients. What if we just take, say, k points in the domain of the function, x1, x2 up to xk, and we take a convex combination of them? How will that correspond to the corresponding convex combination of the images f of x1, f of x2, f of xk? Now what we expect is that the same inequality should prevail there, and that's known as Jensen's inequality. Now again, let V be a real vector space, a non-empty subset of that convex, and f on C to R a function. Now let x1 up to xk be all points in C, lambda 1, lambda 2 up to lambda k in 0, 1 with the sum of these lambda i's, I from 1 to k, being equal to 1. Now, if f is concave, then f of the convex combination of these xi's with coefficients being lambda i's, that is larger than or equal to the sum of lambda i's, f of xi's, I from 1 to k. If it's convex, this time we have the reverse inequality. How do you prove such a result? We know it's true for 1 and 2. When k is 1, well, you have equality. When k is 2, that's the definition of concavity and convexity, whichever case is being considered. How do you prove the general form? Well, you apply induction on k, and that's not a big deal. So I'll just write apply induction on K. Why did we start to consider concave convex functions? What was concerning optimization problems? Well, let's, to be more specific, consider maximization problems. How was the concavity of a function related to that? Does a concave function always have a maximum from R to R? Not necessarily, so it might be just an increasing function. Well, but if it has a maximum, will the maximizer be unique for a concave function? Just concave? Well, not necessarily so. If you just have, in fact, y equals 1, f of x equals 1 everywhere, well, that's concave and convex. It's subgraph and epigraph. They're half spaces in R2. They're both convex. But it attains. But what if it's strictly concave and if it has a maximum, then that's attained at a unique point. Can we extend that to some larger class? Concave functions are rare. I mean, they form actually, if you consider the space of all functions, a subclass of measure 0. So they're rare, but can we extend that to something? Well, do we have classes of functions here which contain strictly concave functions as a subclass? You actually reminded us that should be noted as well. It's strictly quasi-concave functions. So it is actually strict quasi-concavity which guarantees the uniqueness of a maximizer in case the function attains its maximum. Well, and strictly quasi-convex for the minimum, of course, for the corresponding case. So, proposition. We still keep our generality, our concave, convex, and others all defined for functions whose domain is just a convex subset of some real vector space. Here, still so. Now let V be a real vector space. C in V convex, F on C to R a function. Now assume that in the first case, sup f of c, in the red case, inf f of c exists. If that's the case and the function is, say, concave, sup f of c exists, will sup f of c be necessarily equal to the maximum of f of c? No. Well, you can have, for example, here a horizontal line, and you can have something like this, which approaches this asymptotically. This will be concave, in fact, strictly concave, but that will not be the case. Well, if f is, for the first case, strictly quasi-concave, and for the second case, it is strictly quasi-convex, then there is at most one x upper star in C, respectively, x lower star in C, with f of x star equal to sup f of C, in which case this will be the maximum of f of C, and here f of x lower star, that's equal to inf f of C, in which case this will be the minimum of C. Well, at most one means either there is none, so the maximum does not exist, as in this case. Well, if there is one, then it's unique. But the proof of this is very simple. Assume that, suppose there are, well, first let's consider the sup case. So assume that f is strictly quasi-concave. Assume that f is strictly quasi-concave. Suppose x star, x double star are in C, different than each other, such that f attains its supremum at both of them. How would that lead to contradiction? Just take a combination of these, well, say with 1/2. Now, set x bar equal to 1/2 x star plus 1/2 x double star. Will this be in C? Yes, C is convex. But now by strict quasi-concavity of F, we have what? F of x star. Well, this is f of 1/2 x star plus 1/2 x double star. Here our lambda is this. We know this is strictly larger than what? The minimum of the values of f at x star and x double star. But they're the same. In fact, their common value is sup f of C. Is this a contradiction? Sup f of C is an upper bound of f of C, but here, this is in C. We have something in the set f of c which is larger than this, a contradiction. Well, the minimum, the infimum case, that's similar. Okay? It's just the same way. Next. Have you ever seen a discontinuous concave function? Well, a discontinuous quasi-concave function. In fact, any monotonic function is both quasi-concave and quasi-convex. No mention of continuity, just either non-decreasing or non-increasing. You can easily see, well, if you take something, on reals, from reals to reals, well, because a convex subset, that would be interval. Well, then the minimum and the maximum of 2 points, 2 different points, well, actually, if you just confine yourselves to the interval determined by those 2 points, well, then the minimum will be at one extreme, the maximum will be at the other extreme, okay? Well, if they're equal, but any monotonic, non-increasing or non-decreasing function, irrespective of whether it's continuous or discontinuous, wildly discontinuous, step function, whatever, they will all be quasi-concave and quasi-convex. But is there any one? Well, some said we haven't. A discontinuous concave or convex function. What about this? Let's take it on this with real values. This is a convex subset. F of x equal to 1 if x is in the interval 0, 1, open interval, but you have 0 if x is either 0 or 1. That is, you have this graph. Let me draw it in red. But the value at 0 and 1 is this. Is this concave? Well, it's easily seen to be concave, But it's discontinuous at these points. So this is concave. Discontinuous at x0 and at x1. But what you said that you haven't ever seen a discontinuous concave function, there is a big portion of truth there as well. Because the fact is, any concave function, now, well, if we talk of continuity, either we should attach a topology on this and we should talk of topological real vector spaces, which is possible, but we'll not do that. We will not confine ourselves to Euclidean spaces when we talk of continuity. A function defined on a convex subset of some Euclidean space Rn with real values, if it's concave or convex, it is continuous on the interior of its domain. So discontinuities only can occur at boundary points of the domain. So there is actually the truth which the existence of discontinuous concave functions, well, that actually pertains to a class of functions of measure zero, the other of full measure. So we could do the proof of that. I mean, it's reachable to us, but it would take too long. So we will just use this theorem by omitting its proof. Now let C be a non-empty convex subset of some Rn. F on C into R, a function. Now if F is concave, then F is continuous on C interior. If it's convex, then it's continuous on its interior as well, because once you have 1 minus F, that will be concave. If minus F is continuous anyway. We will omit the proof of this. Now that takes us to the third characterization of concavity and convexity. Now that was what? You take any point A, you find the graph, this is f of A, then you draw the tangent line. The tangent line, that should stay above the graph everywhere. But now, that also requires differentiability of this function at each point, because we actually require that this happens at each point. Okay, so well, what we'll do is, and we'll do that also in the remaining characterizations, we will take the one-dimensional case, we will formalize what this condition means in analytical terms, and then actually convert that to the general case, to the n-dimensional case, where the domain is a subset of Rn, where n is larger than 1, transform what we have observed in the one-dimensional case as a conjecture to the higher dimension, and then prove that. We will do it in this case. We will do it in terms of one characterization was, well, f was concave, it was differentiable everywhere, the derivative should be non-increasing everywhere. But what does that mean in terms of general derivatives we know? Well, we'll give a meaning to that and show that that meaning does the job. And then f double prime being less than or equal to or larger than or equal to for concavity and convexity. For that, we introduce higher order derivatives in the general case. And, well, do it there as well, but let's continue on Tuesday at 8:40. Wasn't today the homework day? Yeah.